Hello students, I am Renu Matthew, Assistant Professor, MC Department, ISMR Pune. In the last lecture, we learned what software testing is and how testing efforts contributes to the quality of a software product. In this lecture, let us start with why does software fail? Though computerization has allowed dramatic automation of many professions, software engineering to a great extent is still a human-intensive activity. Humans are fallible beings, so software is fallible. What does it mean? It means since human beings are imperfect, so the software built by us will also be imperfect. Let us consider an example to understand human mistakes. A programmer forgets the possibility of user inputting an extensively long string into a field on a screen, because of which there could be a programmatical mistake. Let us consider one more example of a business analyst introducing a defect into a requirement which escapes into the design and further escape into the code. Let's say we are developing an e-shopping site. The site should support 500 customers simultaneously, but actual peak load should be 1000. Once the load exceeds 500, resource utilization spikes to dangerous levels, leading to reduced response time and reliability problems. So the defect in the requirement may lead to a failure. Let's consider one more example of mistake made by a technical writer of introducing an error on online help screen. Instead of multiplication, help is written to add two numbers. This will work for when both the numbers are 0 or 2. All other cases leads to failure. So errors may lead to a failure, but not always. You can say that a programmer, while designing and building the software, can make a mistake or an error. These mistakes or errors indicates that there are flaws in the software. These are called defects. When the program is executed, the defect may result in unexpected behavior or the system exhibits a failure. Now let us define the terms error, fault, and failure. Error can be defined as a human action that produces an incorrect result. Error could happen because of some confusion in understanding the functionality of the software. It can also be due to some miscalculations of the values. Defect can be defined as a flaw in a component or system that can cause the component or system to fail to perform its required action. The cause of a fault or defect is an error or a mistake by a person, for example, defective programming by the developer. Faults may be even caused by environmental conditions like radiation and magnetism that introduce hardware problems. It is possible that a fault is hidden by one or more other faults in other parts of the program. Defect masking is an occurrence in which one defect prevents the detection of another. In that case, failure occurs till the masking defects have been corrected. This demonstrates that corrections can have side effects. Now let us see whether all defects results in failure. Not all defects result in failures. Some may stay inactive in the code and we may never notice them. For example, defect in dead code will never result in failures. A defect can exist that will not cause a failure during testing, but will always result in failures in production. For example, security, reliability defects, performance defects. The reason being, test environment do not closely replicate the production environment. If the test environment does not mirror the production environment, performance defects cannot be identified. From where do defects and failures arise? It can arise from errors in the software specification. A software specification is a written document which describes the functional and non-functional aspects of the software. It can arise from errors in the design of the software. A poorly designed software can have multiple defects. It can also arise due to errors in the use of the system. Errors in the use of the product may arise because of inadequate knowledge of the product to the testers, to the developers. The tester may not be aware of the functionalities of the product, and hence while testing the product, there might be some defects or failures. The second reason for errors in use of the product may arise because of lack of understanding of the functionalities by the developer. The developer may not understand the functionalities of the product or the application properly. Based on their understanding the feature, they will develop which may not match with the specifications. This may result into defects or failure. Another reason could be because of the wrong setup of the testing environment. Testers may report defects or failures. Hence, proper test environments are required for quality and for on-time delivery of the product to the customers. The defects and failures reported by the testers while testing the product may arise because of intentional damage also. Defects can be there as potential consequences of earlier errors. Errors found in the earlier stages of development reduce the cost of production. So it is very important to find the error at the earlier stage of software development itself. This could be done by reviewing the specification documents or by walkthrough. Above all this, the rate at which people make mistakes increases when they are under time pressure, when working with complex systems, interfaces or code, when dealing with changing technologies, and when developing highly interconnected systems. Now the question that comes to our mind is, how much testing is enough? Let us consider a few pointers. Is it never enough? Is it enough when you have done what you have planned? Is it enough when your customer is happy? Is it enough when you have proved that the system works correctly? Is it enough when you are confident that the system works correctly? It is not so. It depends on the risk for the system being developed. The risk can be risk of missing important faults, risk of incurring failure costs, risk of releasing untested or under-tested software, risk of losing credibility and market share, risk of missing a market window, risk of over-testing and ineffective testing. This means we need to use a risk-based approach in testing. In risk-based approach of testing, we use risk to determine what to test first, what to test most, how thoroughly to test each item, what not to test in the current release, and allocate the time available for testing by prioritization. In short, we can say that prioritize tests so that whenever we stop testing, we have done the best testing in the time available. The testing trade-offs, that means compromises, are done based on contractual and legal requirements of the project and based on industry-specific requirements to be satisfied through the software project. It is difficult to determine how much testing is enough, but it is not impossible. Now let us move on to the 7 testing principles, which are: testing shows presence of defects, exhaustive testing is impossible, early testing is preferred, defect clustering, pesticide paradox, testing is context dependent, and the last, absence of errors fallacy. Now let us consider each of these principles in detail. Testing shows the presence of defects. One of the objectives of testing efforts is to find defects. Testing can show that the product fails, that there are defects. Testing can show the defects are present but cannot prove that there are no defects. Even after testing the application or product thoroughly, we cannot say that the product is 100% defect free. Testing cannot prove that a program is defect free. Adequate testing reduces the probability that evident defects are present in the test object. Even if no failures are found during testing, there is no proof that there are no defects in the application. The second principle, exhaustive testing is impossible. Testing everything, including all combinations of inputs and preconditions, is not possible. Or we can say that exhaustive testing is possible but not practical. We can spend a lifetime and test all combinations of inputs and preconditions, but it's not feasible in project development as it comes with deadlines. So instead of doing exhaustive testing, we can use risk and prioritize to focus testing efforts. Software in normal practice would require an astronomically high number of test cases. Every test is just a sample. The test effort must therefore be controlled, taking into account risk and priorities. For example, let us consider an application with one screen and suppose there are 5 input fields, each having 5 possible values. Then, to test all the valid combinations, you would need 5 raised to 5 tests, that is 78,125 tests, which is impractical. This is very unlikely that the project timescales would allow for this number of tests. Early testing is preferred, the third principle. Testing activities should start as early as possible in the life cycle and focus on defined goal. This contributes to finding defects early. Since the cost of finding and removing a defect increases, the longer that defect is in the system, early testing also means we would minimize the cost of removing defects. If you observe the graph, we understand that if defects are detected in the later phases of software development, greater will be the cost incurred in correcting it. For example, if we have identified some defects during user acceptance testing phase due to wrong requirement specification, it will lead to rework in SRS, design documents, code specification, coding, and in testing efforts, which becomes a very costly affair. The fourth principle, defect clustering. Defects are not randomly or uniformly distributed throughout the software under test. Rather, defects are found in clusters with 20% or less of the modules accounting for 80% or more of the defects. A small number of modules contains most of the defects discovered during pre-release testing or shows the most operational failures. While testing, most of the testers have observed this phenomenon, which basically happens because an area of the code is complex and tricky. Test designers often use this information when making the risk assessment for planning the test and will focus on these known areas that may also be called as hotspots. In a metaphorical way, we can imagine that bugs are social creatures who like to hang out together in the dark corners of the software. Pesticide Paradox, the fifth principle. After a certain number of iterations of testing, as the testing improves, the defect number starts dropping, most of the bugs will be fixed and the hotspot area will be cleaned up. Developers will be extra careful in those places where testers found more defects and might not look into other areas. Hence, by executing the same test cases will no longer help to find more defects. The test cases needs to be revised and new and different test case needs to be written to exercise different areas of the software or system to potentially find more defects. Testing is context dependent. Testing must be adapted to the risk inherent in the use and environment of the application. Different kinds of applications should be tested differently. For example, safety critical software is tested differently from an e-commerce site. Absence of errors fallacy. The word fallacy means misleading notion. If the system build is unusable and does not fulfill the user's needs and expectations, then finding and fixing defects does not help. So the belief, no failures means the system is useful, is a fallacy. With this, we end this lecture. Stay tuned for the upcoming lectures. Thank you.